So it is quite a great privilege to be here talking to you, given a few years ago I was sitting in the audience watching all these amazing speakers coming in and telling you about the research that they did. So it's quite sort of closing the cycle now to be the one presenting. And I'm going to talk today about liquid crystals and how you light up goal-free, which is what I spent the last 2.5 years of my life studying. So the presentation falls into three main areas. First, I'm going to talk about liquid crystals, what they are, a bit about the history, the different phases you can get, and what they're used for. I'm then going to talk about organic light-emitting diodes, affectionately known as OLEDs, so what they are, again, what they're used for, how they and liquid crystals are fitting competitions starting to come together. And then finally, for those of you that are still awake, I'm going to go into the highly technical part on what I've actually been doing for the last 2.5 years of goal-free, and much more on how liquid crystals and OLEDs are really starting to meet. So everyone, I'm sure, is familiar with the two fundamental states of matter: the crystalline solid state, where the molecules have absolute position and orientation order, and the isotropic liquid, where molecules have no order at all. However, between them, for some molecules, lies a fourth state of matter, the liquid crystal phase, where molecules have intermediate degrees of positional and orientational order, which means that, like a solid, the liquid crystal has a particular property known as anisotropy, but like a liquid, it flows. And despite the fact very few people know about liquid crystal phases, they're all around us in nature. In fact, you're probably watching this presentation right now on a liquid crystal display. Liquid crystals were first discovered in 1888 by Cirencester, who, when he noticed that cholesterol benzoate had two melting points. The first melting point gave a cloudy pearlescent liquid, and the second melting point gave a clear liquid. The cloudy pearlescent liquid was later determined to be a novel state of matter, initially called soft crystals, but then the name it's become known by to today, liquid crystal phase. Initially, they were only of academic interest, but in the late 1960s, early 1970s, they were used in prototype liquid crystal display devices, and particularly after 1972, when at the University Hull, the cyanobiphenols group of liquid crystals, with the most famous being 4-cyano-4-pentyl-biphenyl, affectionately known as 5CB, was discovered, which is a room temperature liquid crystal, which meant that liquid crystal displays no longer had to operate at temperatures above 100 degrees. They became actually commercially quite important. And from about the 90s, you would have seen the old bulky cathode TVs being replaced by flat screen TVs containing liquid crystal displays. In order to have a liquid crystal phase, molecules need to have a particular property known as anisotropy, which is where one of the molecular dimensions of the molecule is significantly different to the others, with two most typical shapes being the rod-shaped molecules, where they're much longer than they're wide, or disc-shaped, where their width is much wider than the length. The reason why this is important can actually be considered if you think about what happens when you take typical everyday household objects in these shapes and just drop them from a height onto a surface. If you were to take a handful of pens and pencils and drop them, you will notice that while they don't align exactly, they all more or less fall so that they're in the same aligning in the same direction. Again, take a handful of change, which is a rare thing in these COVID days, and drop them. And you'll notice that the coins fall, so they're facing upwards. None of them will fall on their sides. If we were to replace these by very simple molecules, you've got the most simple liquid crystal phases. Phases where there's some degree of orientational ordering to the molecules, but no positional ordering. The rod-shaped molecules are more exactly called calamitic molecules, and they give rise to a particular set of liquid crystal phases. The most simple of the phases is the pneumatic phase, where the molecules have orientational order, as each molecule tends to orientate so it's facing in one particular direction on average, which is known as the director, but they have no positional ordering. An additional degree of ordering is introduced in some molecules that give rise to synectic phases, where the molecules choose to align in layer planes. In the synectic A phase, the director is perpendicular to the layer plane, while in the synectic C phase, the molecules choose to tilt at an angle to the layer plane. There are also more complex synectic phases with high degrees of ordering, where the molecules position themselves on hexagonal lattices in the layers. In order for a molecule to be rod-shaped and have a liquid crystal phase, you need two things. You first of all need a rigid rod-shaped core, which can be formed by varying numbers of benzene rings or cyclohexane rings. And you also need flexible chains. The rod-shaped cores introduce that stiffness and needed orientation to the phases, while the flexible chains introduce the fluidity that's needed to make it a liquid crystal phase from just a crystal phase. Dish-shaped molecules are more formally called Dyscotic molecules and form their own set of phases. The most simple of which is the Dyscotic Pneumatic Phase, which again has orientational order but no positional order. Compared to the calamitic pneumatic phase, the Dyscotic pneumatic phase is actually rarely seen. Instead, Dyscotic molecules, for some reason, tend to prefer to align themselves in columns. And the columns themselves can either be disordered, in which case you get a columnar pneumatic phase, or they can order themselves on lattice points, with hexagonal columnar being one of the most common. They can also sometimes order themselves on a rectangular space group. In order for a molecule to have a Dyscotic phase, you need to have a rigid central disc-like core, which is normally formed from aromatic rings. And then you need peripheral long chains, which again introduce fluidity to the molecular phase. And these are several examples. One of the most important things about liquid crystal molecules is the fact that they're anisotropic. It gives rise to the phase itself, and this also gives rise to the properties of the phase, with one of them being birefringence. Because the molecules and the phase itself are anisotropic, there are two refractive indices to the molecule: the ordinary or parallel refractive index and the extraordinary or perpendicular refractive index, which in the liquid crystal phase, because of the ordering, can act independently and can result in the splitting of pane polarized light, hence giving rise to double refraction and birefringence. But once you reach the isotropic liquid phase, they average out because the molecules are randomly ordered. This actually can become extremely useful when you have polarizers present. One of the most common methods of identifying if your molecule is liquid crystalline or not is to view it between polarizers which have been crossed at an angle of 90 degrees. This would normally result in complete extinction of light because it is being polarized by passing through the first polarizer and then is blocked by the second polarizer at 90 degrees. However, when you have a birefringent liquid crystal phase, which has two refractive indices, the pane polarized light is split into two ways which travel at slightly different speeds and angles. That means that the pane polarization is lost, and when viewed through polarized at 90-degree angle, you see color. In fact, you see more than color, you see a interference pattern resulted and a particular texture which can enable you to identify what the phase is. And this is something I do with all my samples in order to identify if I've got a liquid crystal phase or not. So the pneumatic phase can be identified by a particular texture, which is called the Schloren texture, which literally means thread-like due to these black optical defects that are present on a color background. And these black optical defects are due to sudden changes of the director in the phase itself, which results in areas of optical extinction. In the synectic phase, because you've got that additional ordering due to the layer planes, you don't get a Schloren texture. Instead, you get what we call a focal conic texture, which is distinguished by these fan-shaped textures, which is caused by the meeting of different sort of directors in the layer plane and converging with each other. The hexagonal columnar phase, depending on how the columns are aligning compared to the viewing angle, can produce either these straight line defects or else these fan-shaped defects. Interestingly, these two textures are actually taken from a copper containing liquid crystal, which falls into a subclass of liquid crystals known as the Metallomesogens, which are literally metal liquid crystals. And these are a few examples of various Metallomesogens that are. It's of great interest to introduce metals into liquid crystals because metals have particular properties. Some of them are magnetic. Transition metals often have more than one oxidation state. So if you introduce them to a molecule, you can introduce redox properties to the molecule. Some of them, such as these platinum-2 complexes, have photophysical properties which are of great interest. You also, in metal complexes, because you've got different coordination chemistries around the central metal atom, you've got more geometries you can play with, and chemists that go into material science tend to love playing about with molecules and seeing what happens when they do that. The very first metallomesogen that was discovered was this Diaryl Mercury 2 complex, which Volder back in 1923, for some reason, decided that he was going to make it and see what it did when you heated it up and cooled it down. I have to admit, quite why you would want to make that and see what it does when you heat it up is beyond me, but he did, and people realized that actually, yes, you could have metal complexes as liquid crystalline, and eventually did an awful lot of exploration. Birefringence also plays a very key role in the major use of liquid crystals, which is in liquid crystal displays, along with another property that comes through to from the isotropy of the molecule, which is the fact that it has two dielectric axes, which results in overall the molecule having a permanent dipole. In a liquid crystal display, and at this point I should stress that these diagrams are highly simplified, you have a backlight, two polarizers at 90 degrees angles to each other, between which you have an aligned liquid crystal phase, typically a pneumatic phase. And then you have electrodes which can apply a voltage across the phase. In the off state, the refractive indices of the liquid crystals are aligned with the viewing angle. So there is no diffraction of the pane polarized light. So no birefringence occurs and the screen appears black. However, when a voltage is applied across the phase, due to that permanent dipole, due to the anisotropic nature of the molecules reorientate themselves. So the line of the refractive index changes and sudden and pane polarization is lost, allowing passage of the backlight through the display. And it was fairly revolutionary when people realized that they could actually use liquid crystals to do this. And today they are widespread in things like TV screens, computer screens, mobile phone screens, calculators, and various other things. However, while for about 2 decades they were completely unchallenged in the domination of the screen technology, they have since started to gain some competition from OLED screens. Organic light-emitting diodes, or as I tend to call them, OLEDs, because it's a bit less of a mouthful, are the organic equivalent of the inorganic light-emitting diodes, LEDs, which most people are more familiar with. And they work by the phenomenon of electroluminescence, which was first discovered in 1907 in silicon carbide. It wasn't until 1955 that the first organic example was recorded in acridine orange and quinoacridone. My apologies if I pronounced them wrong. And inevitably, once they discovered that, sooner or later someone tried to put it in an LED in 1960s when a group of chemists at Dow Chemicals managed to come up with a prototype OLED. Unfortunately, it wasn't very practical because it required voltages of over 100 volts to actually work. So nice try, showed it's feasible, but personally I wouldn't want to use it. It wasn't until 1987 that Tan and Van Slyke finally managed to actually get a practical device using tris 8-hydroxyquinolatine aluminum free, which not only gave a lovely green light, but also proved to be able to operate at voltages below 10 volts, which made it practical for use. And since then, there have been further developments and they've become commercially viable. OLEDs work by the absorption and the emission of light. Most molecules in nature are found in the ground state, which is the lowest energy state of the molecules. It's the one they're most stable in. However, on absorption of light that is of equal energy between that ground state and a higher energy state, the electrons from the excited state are promoted up into this higher state. But they're not terribly happy in their long term because it's of a higher energy than that stable ground state. So the electrons want to get back down from that excited state to the ground state. And there's several ways they do this, one of which is by emission of light of a slightly longer wavelength than the absorbing wavelength. And if that energy gap is in the visible region, we see light emitted. There is a slight complication due to whether a state is singlet or triplet. Electrons have an innate spin of a half, but they can spin in different directions, either effectively clockwise or anti-clockwise. This means when you get two electrons pairing up together, there's two ways they can pair. They can even pair where the spins are anti-parallel to each other, giving an overall spin, so the spins cancel out, giving an overall spin of a half, which is a singlet state. Or they can align so their spins are parallel and give a slightly lower energy triplet state with an overall spin of 1. In most organic molecules, you're only really bothered with the singlet states because the ground state of molecules is almost always a singlet state itself. The absorption and emission of light is governed by a series of rules known as the selection rules, the most important of which is the spin selection rule, which states that the overall spin after absorption must, when moving between different energy levels, must be conserved. It's the equivalent of saying energy after doing an action must be conserved overall. And which means that typically from singlet states, you get singlet excited states, and then you go back to singlet ground states. However, there is a saying that rules are made to be broken, and this selection rule, like all rules, in science has an exception. And this exception is when you get heavy metal atoms in the molecule. Due to relativistic effects giving rise to a phenomenon known as spin-orbit coupling, these molecules can flip their electron spins, which means that you can gain access to the triplet states. So while fluorescence occurs from singlet states, which is generally pretty prompt, the equivalent emission of light from triplet states is phosphorescence, which is traditionally distinguished by being over a longer time period than fluorescence. And these are both important to how OLEDs work. So how OLEDs actually work is you've got two bands. The lower one is filled and is affectionately called the HOMO, otherwise highest occupied molecular orbital. The higher one is unfilled and is known as the LUMO, the lowest unoccupied molecular orbital. And there is an MHG gap between the two. The cathode injects electrons into the LUMO, while at the same time the anode is removing electrons. This results in electrons up in the LUMO and electron holes in the HOMO, which pair together to form an exciton. Inevitably, when you get energy imbalances, they want to rebalance themselves, and this is done by emission of light to get back down to the stable ground state, which regenerates the electron. Sorry, the OLED ground state, ready to go back to the beginning of the cycle. This means that the simplest OLED device you can get is literally a cathode made of some type of metal, typically something like aluminium, your emitting layer, which will quite often be a photophysically active molecule, normally doped onto some sort of polymer, and then a transparent anode made of indium tin oxide, which has the wonderful properties of being conducting while transparent, and then a substrate to mount it on, typically something like glass, though plastic can be used if you want a flexible OLED. In real life, it's a little bit more complicated because you have several additional layers. For example, you might have your cathode, an electron injection layer, electron transport layer, a hole blocking layer, then you get your emissive layer, and then you've got several more before you get to the anode. And this is literally just to make sure that you have the most efficient transport of charge from the cathode through to the emissive layer, and from the anode through to the emissive layer, and that electron-hole recombination is isolated in that emissive layer. It can be thought of a bit like a waterfall. You have the same energy gap from the top to the bottom, but you can have different cascades which just break up that energy gap. And overall that results in more efficient transport of energy from the top to the bottom. So why are we interested in the triplet states? Well, it comes down to the fact that injection of electrons and removal of electrons process are independent of each other, which means that there is no correlation between the spin of the electron in the LUMO and the spin of the electron hole in the HOMO. So, and they pair together to form either singlet excitons or triplet excitons. But statistically, triplets are formed in a 3-to-1 ratio to singlets, which means if you've got a molecule that can only access the singlet states, such as a solely organic molecule, you can actually only access 25% of your total energy. However, if you have a molecule that can access these triplet states, suddenly you can access the other 75% of the electrons you're injecting into your OLED instead of wasting them as heat, which means your overall device efficiency is 100% instead of the inherently limiting efficiency in a singlet device of 25%. Which means that most people will now be looking at complexes that contain a heavy metal atom when they're developing OLEDs, because you can increase the efficiency of the device quite easily. OLEDs have now entered the market, but they have yet to take over LCDs, but they will shortly. The reason why they do have is because they have certain advantages over OLEDs. They have a faster response time and improved color contrast because it's a directly emitting layer instead of being a backlight and two polarizers. They're also thinner with no back, partly because they don't require a backlight or polarizers, which makes them lighter. They also have a lower power consumption than LCDs and improvements in viewing angle and the contrast ratio. The reason why they have yet to actually fully compete with LCDs is because of several major issues. The first is that operational lifetime is shorter, and that is just simply because organic molecules are not as stable as inorganic molecules when you're cycling between two different energy states, particularly in blue OLEDs. That's a very high energy transition. So you can very, very quickly actually burn out your molecule, so it will no longer absorb and emit light. Which leads to the second major disadvantage of OLEDs is color decay, because your blue OLED is going to decay in the pixel is going to decay at a faster rate than your green and red OLEDs. So you're sort of steadily going to have your color shift more towards those two and lose the blue. They're also currently lower resolution, and they cost more to manufacture, though this last one will come down as the technology improves. They're also non-recyclable, unlike LCDs where you can recover the liquid crystal layer from the layer, which is an issue because quite often the OLED photophysically active material contains precious metals. However, they are starting to take over the market, so there is a certain element among liquid crystal scientists of, if you can't beat them, join them, because liquid crystal OLEDs actually have a few advantages. The first is a liquid crystal phase is an inherently ordered phase, which means you can order your molecule in that phase, which will actually lower the overall voltage and increase the efficiency of your device, because the charge is able to move more easily through an ordered phase than a disordered phase. The long flexible chains on liquid crystal molecules, which are needed to induce the liquid crystal phase, also are useful in photophysically active materials, because they act as spacers that keep the molecules that little bit further apart, which prevents what we call self-quenching, which is basically where your excited electrons manage to have other routes besides that emissive light emitting transition that we want, where they can deactivate themselves. The fluid nature of the liquid crystal phase can also allow dynamic effects and even self-healing sometimes. And potentially you can polarize the emission of liquid crystalline OLEDs, so you no longer need a polarizer, which increases the efficiency of the device and hence uses less energy by 50%. So it is something that is a very active area of research at the minute. Currently, most OLEDs you'll find that are commercially out there at the minute are based around these yttrium-free complexes, where you have these phenylpyridine molecules with varying shrubbery in order to give different colors. However, there's several types of complexes that are being very actively researched at the minute. One of the most major is platinum-2 complexes. So these are platinum atoms that have lost 2 electrons to give the 2+ oxidation state. And this type of cyclometylated complex has been known for a very long time to be photophysically active, and there is a very wide body of research on them. Of more recent interest, so we're talking the last 20 years now, has been gold-free complexes of this form. Gold-free is what we call isoelectric with platinum-2, because it has the same number of outer electrons in its shell, which means that since they tend to have similar properties when they have the same number of electrons in that outer shell, that people sort of looked at the wide photophysics of platinum-2 and went gold-free, so that's a gold atom minus 3 electrons to give a +3 oxidation state, should in theory have that wide photophysics behavior too. And it's this type of complexes that I've spent the last 2.5 years working on. The reason why platinum-2 has been known about for a long time, but gold-free has only really been studied in the last 20 years, is just simply because despite people's best attempts, gold-free just wasn't photophysically active until then. And it turned out to be due to the fact that when you, in most gold-free complexes, when you absorb light from your ground state up to your excited state, the easiest way for it to get back down to that ground state is actually via DD metal orbitals on the gold ion without emitting light. So it'll just sort of go up to that excited state and it'll just trickle down through this deactivating intermediate state. However, it was discovered that when you put a strong, what we call a strong ligand on it, such as this phenylacetylene ligand here, you could increase the energy of these metal orbitals, so they were no longer, so that route where it could just trickle back down to the ground state through them was no longer there. So instead, when you excited these complexes, you would excite them up to the excited state, and then they would emit back down to the ground state. Hence, you've lit up gold-free. In one of my supervisor's previous PhD students, Dr. Rachel Parker, did a lot of work on this type of gold complex. And she discovered that when you put these long chains on them in the 4 position and the 3-4 position, depending on the length and number of chains on this phenylacetylene ligand, you could get columnar liquid crystal phases. She also showed that they could be used in prototype OLED devices, giving both yellow and green emission in a collaboration that the group has with a group over in China. So when I came in, it was decided that I was going to see what happens when you put the chains on this CNC ligand here in different places. What does that do to the liquid crystal properties? What does that do to the photophysics? So before I finish, there's a few people I need to acknowledge. First and foremost, I need to say a huge thank you to my supervisor, Professor Duncan Bruce, who has guided me and given me advice and loads of useful help throughout the last 2.5 years. I also need to thank my independent panel member, Dr. Jason Lynham, who provides additional support on my PhD and has also provided training and plenty of useful advice on the working with these gold complexes. Dr. Rachel Parker did the previous work in the group on these gold-free complexes, and her thesis has been absolutely invaluable to me. There are several other technical members of the department and other members of the group who listed on the screen who have given me help and training or done measurements for me on instruments I'm not trained to use or they don't let me touch. So I need to thank them too, and generally the rest of the E14 lab, which is the York Molecular Materials group, for generally being supportive. My funding has been provided by a studentship from the Department of Chemistry from the University of York, so huge thanks to them for letting me do a PhD. Johnson Matthey has kindly given us some very generous gifts of gold-free salts, which is saving the group a lot of money. As you can imagine, it's expensive chemistry to do. And I have been making use of the Viking cluster, which is a high-performance computing facility provided by the University of York. Thank you for listening. Do you have any questions?
Can I start off by saying, I do hope, Richard, that we'll have this in due course, because there's a lot of this I've had to look at least twice more, I think, to make sure I understand it. But it is a fascinating talk. There's one small point, Alice, that I was going to ask. You mentioned at one stage the problems of OLEDs in terms of recycling, because this is something that I think all of us are getting more and more interested and concerned with. Could you elaborate just a little on that?
So I think currently it's largely a problem with, though I'll admit I have largely not looked in, I haven't looked into it in great depth, but I think it's largely a problem in sort of extracting the emissive parts of the OLED from the polymer and in sufficient yield to make it commercially viable. And though obviously, if you're going to be putting things like gold complex in there, even if the doping is at sort of about 5 weight %, 10 weight %, that's still, if you're making multiple of these devices, a significant amount of gold that's actually going in there that you're going to really, really struggle to get back. So I think it's an area where the people that know much more about it than me are currently doing an awful lot of work on, because I know it's hard enough getting gold back from things like mobile phones at the minute as well, which is another area which there's an awful lot of work going on to find out how to actually properly recycle them.
Okay, thanks very much. Yeah.
I have a question, Alice. Thank you very much. That was a wonderful talk. And I have to say that clearly you know your subject very well, because you explained it with such lucidity for people who don't have a grasp of the finer points of liquid crystallography. And I thought it was actually brilliant. I just wondered whether there was any indication for these crystals in spectroscopy, in furthering spectroscopy.
I'm not sure if there is. It's not an area I've looked into, though I imagine there is. Someone will probably look after it. I do know that sort of some minor uses is that some liquid crystals will actually change color depending on the temperature.
Yes.
They're using things like thermometers. They're also will be used in sort of engineering projects in order to identify where there's stresses and strains when you're making things. So that's a bit more a niche area. But I haven't yet come across any use in spectroscopy. So if it is there, I imagine it's something that someone will be actively investigating if they think there's a use.
Yes, and perhaps a more mundane question. It seems that television screens are getting better and better definition and better color. Is this because of your work or the work that's gone before you, do you think? Or is it the use of OLEDs?
That's come before.
The use of OLEDs in television screens.
Yeah, so most television screens you'll be seeing at the minute are liquid crystal devices. Only the very, very top range of television screens are currently OLEDs because it costs an awful lot to manufacture them at that point.
And you, if I may come in, they also, according to your comments, decay quicker. So the life of the set would not be as long at the moment, anyway.
At the moment.
Yes, you do see televisions being advertised as new OLED screens, but from what you're saying, that means that you ought to be careful buying those because they may not last very long, or at least the blue may not.
I have to admit, I would be a little bit worried about buying an OLED screen at this point in time because it's much newer technology. So as time goes on, it will definitely get better. But at the minute, the liquid crystal displays, they've been around longer. We know more about them. Part of the reason why the resolution of them has increased is just simply because there's been an awful lot of work that's gone into sort of, and I'll admit it's not an area I know too much about because I know the basic principles, but I'm a bit more interested in what's going on in that layer that does the business rather than all the electronics. But I do know that there's some very fancy stuff they do with sort of the switching of the different pixels. And then there's also various polymer layers they can sort of put on to help improve viewing angle and contrast ratios. So there's a lot of clever stuff that they've come up with. And I imagine some of that stuff is also being transferred over to the OLED devices and new stuff is also being developed for them.
I was wondering, do you actually get involved in trying to apply voltages across these things and seeing whether they change, or are you at a more fundamental physics layer than that?
So I'm very much of making the stuff, but people are then going, who are a bit more on the technical side will then go and do it. So I'm a synthetic chemist.
Right.
I'm interested in making stuff, seeing what it does. Before COVID came along, I was actually supposed to go out to China and work with the group we got a collaboration out over in there and put my complexes into actual proper working OLED devices, which, according to Rachel, who went out there with her complexes, involved an awful lot of sort of watching and being asked questions because they wouldn't actually allow her to do anything, but they didn't know anything about liquid crystals. So kind of needed her to be there to answer all the questions. So I think we don't know what we're going to do at the minute. We've got a grant which is sort of still valid to do that, but I do not think I will be going out to China anytime soon. So we're probably going to be doing a bit more sort of posting things off and doing some Zoom calls. But the hopeful aim is to see what happens when I put my stuff in OLEDs.
Okay, I was actually wondering what the voltages are. You say that they require lower voltages than ordinary LEDs. What sort of voltages do they require? How much difference does it make?
I don't know what ordinary LEDs work at.
Well, red ones are about 0.8 of a volt up to 1.2 volts, and then blue ones are quite a lot higher, up to about 3 volts. I
suspect it might be similar. But again, it's something I have not had much reason to look into at the minute. I've sort of been spending a bit more time figuring out how to actually make things and why they're doing funny things than the actual nuts and bolts of the application at this point.
Yeah.
And of course, things have been derailed a bit because of lab shutdowns due to COVID lockdowns. So I'm a bit behind where I had expected to be at this point as well.
Yep. Yep.
Have you found, sorry, have you found,
is it Alice?
Yes.
I'm sorry, I came in very late. My name's Derek. I used to be in the electronics and semiconductor industry a long time ago.
Yeah.
Am I right in assuming that every individual pixel on a screen has to be, there's a matrix of connections behind this? What sort of spacing is there between these conductors?
I have to admit I'm not entirely certain, but I know that for some of the most modern ones, I think it might be on the nanometer scale.
Yeah. So each pixel is individually addressed.
That's right. Yes, the array, the actual screen has built into it the addressing electronics, so that you basically have all the decoding in the control layer at the back of the screen.
Yeah, and is that a semiconductor array, or is it an array of actually metal connections? Any idea?
Yeah, well, it depends. There are different ways of doing it. They're trying to build the electronics actually into a semiconductor layer, but obviously that's more expensive and complex. But
yeah,
you can do.
But it's quite remarkable.
It is. It is. Yes.
Yeah. Yeah, I have to admit, the first time I realized what was actually behind the liquid crystal display devices, how they work, and I have to admit I haven't still quite wrapped my head around some of the technical details, because they can do some absolutely amazing switching patterns now. It was sort of, they can actually do that, and there's how many pixels that they're doing that to?
Well, the stunning thing is that you get that many pixels and they all work.
Yes.
Or mostly. You occasionally get one that doesn't, but
actually that's something that used to happen many years ago. You get a screen with some blank pixels.
Yeah,
doesn't happen anymore.
Yeah, occasionally, but very rarely. Because of the purity and the manufacturing processes are that much better. Yes.
Yeah. In actual fact, it's another reason why OLEDs have sort of still struggling to get fully into the market, is because they still can sometimes suffer from pixel burnouts because of the high energy transitions. You're basically degrading the organics. And I think I came across, when I was doing some research, that you can sometimes burn a picture into them by accident.
Well, like in the old days, the old fluorescent screens, you used to get that. Screensavers will be back again.
Yes, that's true.
I was interested to hear you talking about the synthesis of these chemicals. So actually you are doing chemistry in working out how to create some of these amazing shaped molecules.
Yeah.
Yes, I'm making them, and sort of, we're a very heavily synthetic lab in the molecular materials lab. So there's some of us working on making liquid crystals, and there's some other people that are working with proteins, and we've got some people that are working with sort of other photoemitting devices and stuff for solid state batteries. So we all sometimes end up having moans to each other about, my column has co-eluted again. I got 5% yield. I don't know what's going wrong. I can't get rid of that purity.
Yes. Well, yeah, presumably also knowing what it is that you've got at the end of it, working out which molecules are there and what shape they are.
Yeah, there's been a few times where I've sort of been looking at an NMR going, I think it's this. I'm pretty certain it's this. And then a few weeks later, it's also, it wasn't that. It was this. Oops.
Yeah. Yes, you can't really tell by looking at it. Yeah, I did wonder about the beautiful pictures there, which were gold in color. Are they actually gold in color, or is that because of the way you're viewing them?
They are actually gold in color. So the ones in the sort of final part, which were taken of the gold complexes, there's two reasons why liquid crystals phases can be coloured. One is birefringence. So the texture I showed in the pneumatic phase, that was pure birefringence. The compound itself was white. But the beautiful yellow pictures, that's largely because the compounds themselves are yellow, which means that the colour of the phase is sort of being carried through to the picture I'm taking. And the two I took of the copper complex, the reason they're predominantly blue is because the copper complex itself was blue.
Okay, so that is actually related to the fact that the gold, for example, is gold coloured, and obviously a lot of copper complexes are blue in colour.
Yeah, and I've been doing some work with some liquid crystalline porphyrins, and I don't know if anyone's ever come across porphyrins before now, but they are purple in the solid state. They are this really bright claret red in solution. I mean, if you've got porphyrin somewhere in solution, you know about it because your porphyrin is pink. Your solvent is pink, even if you have put an awful lot of DCM through the rotovap to try and clean up that porphyrin that you accidentally splash all the way through. So and the liquid crystal phase themselves, it's a really, really intense red. So that's again the color of the porphyrin is influencing the color of the phase.
So does that mean to have a multicolored display, you have to have a lot of different chemicals in there, or you've got to...
So there's some ways you can do it. So sometimes you will have the birefringence will be given the color. The two I think it's typically done in screens is to get the different pixels, is you actually have filters that sort of are busy providing the different colors. Though I have to admit, I'm not entirely certain how they use those filters. I just know that there is a way that they produce the colors.
Any other questions from anybody? Can't see. We've still got over 50 people, I think, in. Yeah. Anyway, if there are no more questions, I'd like to thank you very much again, Alice, for giving us a fascinating talk. It really stretched my chemistry from a long, long time ago, beyond, I think, beyond its breaking point, more or less. So I'm going to have to look forward to when we see this lecture up online, which I think will be fascinating. Thank you very much. I think we can thank you in the normal way. I'll just do it like that anyway. Thank you very much, Alice.